right, so the next section under the discrete time arc of change that we want to consider is the eigenvalue representation of the n-step transition probabilities. Okay, so why do we need the eigenvalue representation of the n-step transition probabilities? Now take note that sometimes the calculation of the n-step transition probabilities may become difficult to deal with as the number of steps or transition becomes very large. So for instance, suppose we want to find if the probability that the chain visits the future state will converge as the number of steps or transition increases. An easy way to do this is to have a representation of the n-step transition probability matrix so that the limiting probabilities can be derived, okay? In other words, we want to find out if the probability of finding a Markov chain in a specified state in the long run will exist or not. So in our subsequent tutorial, we shall consider cases where the limiting probabilities exist, and we will show how they can be computed, okay? So there's a theorem which states that if the transition probability matrix has distinct non-zero eigenvalues, then we can express the transition probability matrix in the form as defined in equation 1. So equation 1 is basically the eigen decomposition of the transition probability matrix, which is basically a type of decomposition that involves decomposing the transition probability matrix into a set of eigenvectors and eigenvalues. Okay, so the Q is a square matrix whose ith column is the eigenvector, and this D here is the diagonal matrix whose diagonal entries or elements are the corresponding eigenvalues. Okay, so based on equation 1, it can be deduced that the eigen decomposition of the n-step transition probability matrix can also be obtained by using the expression in equation 2. Okay, so equation 2 is showing us the eigen decomposition of the n-step transition probability matrix. So let's take an example. A Markov chain with two states has a one-step transition probability matrix defined below. We want to find the eigen decomposition or the eigenvalue representation of the n-step transition probability matrix. So how do we do this? Let's take a look at the solution. So we first have to find the eigenvalues of the transition probability matrix, which are going to be the roots of the characteristic equation defined below. Okay, so we can express this in this form, which is going to be a determinant of 2 by 2 matrix. And we know that we can take the product of this minus the product of that. Okay, so that's how we get the determinant, okay, which is going to be of this form. So once you work this one out, you are going to obtain this, which looks like a quadratic equation. Okay, so we know the quadratic formula, right? So this is going to be like the quadratic formula. So we have the coefficient of A to be 1, the coefficient of B to be that, and the coefficient of C to be that, okay? So this is going to be the coefficient of 1. So the coefficient of A is going to be 1. This is the coefficient of B, okay? And this is the coefficient of C. So that's once you try to input these values in this equation, you have your first eigenvalue to be 1 and second eigenvalue to be 1 minus beta minus alpha, okay? So therefore, the corresponding eigenvector Q index 1, when our eigenvalue is 1, can be obtained using this expression, which is similar to that, okay? So we want to work out for these values, x1 and x2. So we can pick the first row, multiply by this column and equate it to x index 1, or we can pick the second row here, multiply by this and equate it to x2, okay? So I'm going to go by the first approach. So once you pick this, multiply by that, equate it to x1, you're going to have this. You can expand to have this, then you can group like things. And once you work this out, alpha will cancel alpha. So you have x2, the coefficient to be 1, and the coefficient of x1 to also to be 1, okay? So our first eigenvector is going to be of this form, right? All right, so the corresponding eigenvector Q index 2, when our eigenvalue is 1 minus alpha minus beta, can also be obtained using this expression, which is similar to that, okay? So in here, I'm going to pick the first row, multiply by this column and equate it to that, the product of that, okay? Or you can also pick this, multiply by that and equate it to the product of that, okay? So once you try to expand, you obtain this, you group like things, you obtain that, and you can rearrange this to have that so that the coefficient of x2 will be minus beta and the coefficient of x1 will be alpha. So our second eigenvector is going to be of this form, right? So therefore, we can have our square matrix whose ith column is going to be the eigenvector. So this is going to be the first eigenvector and the second eigenvector, okay? And we can take the inverse of this to have that. Okay, so this will be the inverse of this, I hope you know how to get an inverse of a 2 by 2 matrix. And this is going to be our diagonal matrix whose diagonal elements are the corresponding eigenvalues. Okay, so we can then um, get the eigen decomposition of the transition probability matrix, which can be obtained in this form. So we have our Q, we have our diagonal matrix, and we also have our inverse of Q. Okay, so we can rearrange this in this form. Okay, so we are interested in the eigen decomposition of the n-step transition probability matrix, which can be obtained using this form. So we know that the n will have effect on the diagonal matrix. 1 raised to the power n is the same as 1, 0 raised to the power n will be 0. So we have this raised to the power n, okay? So we want to work on this two, the product of these two. So we pick the first row, multiply by the column, okay? So once we do that, we obtain this, then we pick the first row, multiply by the second column, we obtain that. Now we're going to pick the second row, multiply by the first column, we obtain that. And we pick the second row, multiply by the second column, we also obtain that, okay? So we also take the product of these two. So let's pick the first row, multiply by the first column, we obtain that. The first row, multiply by the second column. Then we can also pick the second row, multiply by the first column, we obtain that. Then the second will multiply by the second column, you're also going to obtain this, okay? So we can rewrite this in this form, right? So that once we multiply through by 1 divided by alpha plus beta, we're going to obtain this result, okay? Which is going to be the solution, okay? So this is going to be the eigen decomposition of the n-step transition probability matrix. All right, so another example, the officers of a certain ministry have grades 1, 2, and 3. Each officer's grade is reviewed annually. Movement between grades being according to a Markov chain with one-step transition probability matrix given below. So this is a transition from grade 1 to itself, the transition from grade 1 to grade 2 in that order, okay? So these are future grade and our current grade. So X index N is an officer's grade after N years of service. Now, if each officer enters the ministry in grade 1, we want to show that what is the probability that an officer's grade is 3 after N years of service, given that each officer enters the ministry in grade 1. We want to have a representation of it in this form, okay? So how do we do this? Let's take a look at the solution. So we first find the eigenvalues of the transition probability matrix, which are going to be the root of the characteristic equation defined below. So we can also represent this in this form. So how do we get a determinant of a 3 by 3 matrix? So let me show you something here. So this is a determinant of a 3 by 3 matrix, and we can use this approach to get the result of interest, okay? So if we use this on this one, we're going to obtain this, okay? And once you work this one out, you have your first eigenvalue to be 1, your second eigenvalue to be 1 out of 3, and your last eigenvalue to be 1 out of 4. Or basically, you can even use a calculator to get this result, okay? All right. So the corresponding eigenvector Q index 1, when our eigenvalue is 1, can be obtained using this expression, which is similar to that, okay? So let's work on the second row. We take the second row, multiply by this column and equate it to X index 2. So this is what we're going to have. You group like this, you have this main work things out. We have the coefficient of X2 to be 1 and the coefficient of X2 to be 1, okay? So now I want to work on the first row, okay? So we pick this first row, multiply by the column and equate it to X1, okay? So that's what we have once you try to group like things. So we pick this to the other side, we obtain this. Now we know the value for X3 to be 1, the value for X2 to be 1, okay? So we are looking for X1, so X1 is 1. So our first eigenvector is going to be of this form, right? Similarly, the corresponding eigenvectors Q2 and Q index 3 can also be obtained if we use similar approach, okay? If we use similar approach, you're going to get this result for the second eigenvector and the third eigenvector, okay? So therefore, the square matrix whose ith column is the eigenvector can be obtained. So these are first eigenvector, second eigenvector, and the last eigenvector. And you can also obtain the inverse. You can use the calculator, scientific calculator to obtain this inverse, okay? And we are going to have our diagonal matrix whose diagonal entry is the corresponding eigenvalues, okay? All right, so once we have this, we can get the eigen decomposition of the n-step transition probability matrix in this form. So we have our Q, we have our diagonal matrix raised to the power n, and we have our inverse, okay? So let's take the product of this and this. So we take the first row multiplied by the column. We have this first row multiplied by the second column and the first row multiplied by the last column, okay? And we can pick the second row multiplied by each of the columns. So second row by the first column, second row by second column, second row by the last column. And we can also pick the last row by first column, last row by second column, and last row by last column, okay? So now we're also going to take the product of these two. So first row by each of the columns. So first row by the first column, first row by second column, first row by the last column. Then we pick the second row by each of the columns. So second row by the first column, second row by second column, second row by first column. Then we pick the last row by each of these columns. So second last row by first column, last row by second column, and last row by last column. Okay. So basically, we are interested in the probability that an officer's grade is 3 right after n years of service, given that each officer enters the ministry in grade 1 at the initial time, okay? And we can rewrite this form, okay? Now, we already know the n-step transition probability matrix for this, okay? So using the idea of Chapman-Kolmogorov equation, we know that the first index here is the current state and the last index here is the future state, okay? So from our n-step transition probability matrix, we just pick the first state and the future state, which is 3. So the current state 1 and the future state 3. So this is what I mean. So we have the current state 1, 2, and 3, and the future state 1, 2, and 3. So where they intersect, the current state 1 and the future state 3 is where they intersect, where we are interested in this value, okay? So that's basically what we're going to obtain. And we can rewrite this in this form, okay? Which is going to be the solution of interest, okay? All right, so this will be a trial question. I will leave the solution in the description of this video so you can check it out. Please, if you find value in today's tutorial video, don't forget to subscribe if you have not. And thank you for watching.